Hello, good morning, sir.
Hello.
Hello, how are you, sir? You are not audible, sir.
Hello.
Hello, yes, sir.
Yes. Okay.
So, sir, just wait 2 to 3 minutes, sir. The
Sure.
participant, more participants that will join. So, good morning to all the participants. So, I warmly welcome each one of you to the 8-day faculty development program on this deep learning organized by E&ICT Academy, MNIT Jaipur. So it is great honor to have esteemed speaker. Now today he is with us, Dr. Satyendra Singh Chauhan. So for this insightful journey, and we are confident that this program will foster meaningful learning, collaboration, and innovation in the field of deep learning. So before start the lecture, let me introduce Dr. Satyendra Singh Chauhan. Dr. Satyendra Singh Chauhan earned his PhD in Artificial Intelligence from Computer Science and Engineering at the Indian Institute of Technology, Roorkee, where his research focused on finding out algorithm solutions for AI planning problems. His research area include emerging techniques in AI such as continual machine learning and open world machine learning. His innovative work has been published in several renowned international journals, contributing significantly to the academic discourse in his field. He has more than 7 years of experience in academics and research. Before MNIT, he worked as an assistant professor at SGSITS Indore. He is a senior member of IEEE and he has been a reviewer TPC member of international conferences and reputed journals, including IEEE Transition and many more. He is currently executing various research projects sponsored by different government departments and industries such as DRDO, DST, National Supercomputing Mission, and the government of Rajasthan. He has supervised 4 PhD and 9 MTech students, and currently he is supervising 5 PhD students and 3 MTech students. So now I welcome you, sir, here in the this FDP. This is the second last day of this FDP.
Okay. So, am I audible?
Yes,
Voice
sir.
is clear? Okay.
Yes, sir.
So, let's start. So, thank you for the introduction. So,
Thank
I'm sharing my screen.
you. Yes.
Okay, so I hope it is visible to all of you.
Yes, sir. Yes, sir. Yes, sir.
Let's start.
Yes.
So, from this session, what we are planning to do. So, I'll talk about briefly about generative AI, though you indirectly have touched upon in GAN lecture, generative adversarial lecture. Then moving to, we'll see one of the emerging model called diffusion model. So we'll talk about how diffusion based model works and what is the intuition behind it, and how they are different from other generative models that you have seen and what other that you have not seen. I'll give you intuition about all those models, and then we'll discuss the diffusion based model. And towards the end, we are going to see hands-on, or I would say a demo on diffusion model. So I'll share a notebook and I'll explain how the theory meets to the hands-on, and we are going to see how it works. Okay, so let's start with introduction session. Though you have might have seen this, so I'll quickly jump over it, and whenever you feel that I should elaborate, then you can just and just write in the chat the question. I'll respond immediately. So if we talk about, so you have might have studied, and during those initial sessions you might have understood what is supervised learning, unsupervised learning. So given a data, you have a label to supervise learning. So you try to learn a function that maps from X to Y. And you have seen the various examples like classifications. For example, whenever you receive an email on Gmail, it automatically goes to either primary, social, promotion, or update category. So this is an example of classification. Regression, where you are trying to predict a number. Object detection, semantic segmentation, all comes under the supervised learning. And another category called unsupervised learning, given only the data, no label, you try to learn the underlying structure, pattern in the data. So how many similar types of data are there? So basically, you try to come up with clustering and other some algorithm that comes under the dimensional reduction, where you try to reduce the dimensions. So this was, and machine learning or deep learning, we perform those classification or regression or other various tasks. When we talk about generative AI, so basically, overall goal of our in deep learning, machine learning, that given some input data, and that input data might be not only one feature, it might be number of features you have, or it could be an image, it could be a text, anything. So any type of data, it could be an audio. The function is basically the model that maps from X to Y, and if the Y, basically you are predicting whether it is a number or a class or maybe a probability, it is giving a discrete value, so then it is not a generative AI. So when we talk about generative AI, so Y is something that is generated from training data. It could be a natural language like text, like GPT models are generating, or Llama models, or any other Grok model is generating text. It could be an image, it could be an audio, video. So if there is a data is generated, and given some training data you have, then we can categorize it to generative AI. Though it is not in formal definition. So informally, we call those models generative AI. Formally, when we say models of two types, generative and discriminative. So when we talk about supervised learning, where you try to predict some class or some output Y, given some X, then this models basically calls the discriminative models, which basically can be represented simply by a conditional probability. And or in case of generative models, in generative models, we try to learn the distribution of the data. So, and once you learn the distribution of data, you can generate new samples. So they have a complementary role in artificial intelligence. So till now, in most of the sessions, unlike generative adversarial network, you have gone through the discriminative models, and whereas generative models, we try to learn the distribution of the data. So basically, what is generative modeling? So you given some training samples from some distribution, so they might be following some distribution, and the whole idea is to learn another model, so learn a model that represent the same distribution. So basically, uh, given some training data, let's say X, and it follows some distribution, probability distribution. Let's say we are denoting it as P data of X. Then once your model is learned, the model learns some distribution. Let's say denoting by P model X. Then the whole idea of generative AI is that how we can learn the probability distribution of data that is similar to original data. So one thing is clear, what that we have to learn the distribution of the data, right? Now, but uh, how we can learn? So to understand this, to get the intuition of all the generative AI, let's begin with a toy example, a simple example. Let's take an example. Suppose you have these data, you have these numbers. When I say I want to generate, which is similar, right now having some numbers, and I want to generate numbers which are like some similar to this. Similar, example, So now is it clear? I have removed the background noise. So now is it clear? Yes. Okay. So when we talk about similarity among the data, so again starting. So given some numbers, a simple toy example, taking a small example. Let's say we want to generate a new data. New data means new numbers which are similar to these numbers. And when we talk about similar to these numbers or similar to some data, then what do you mean by similarity? So basically, we want to generate some numbers which are having the same distribution that these numbers have. And when we talk about distribution, probability distribution, if you want to learn the probability distribution of this data, then how will you do it? What is the idea? Any suggestion? How we are going to learn the probability distribution of this data? So basically, we can estimate of this data by calculating two things: mean and standard deviation. So where the center of the data is and how much it is spread, assuming it following a normal distribution. So let's say, so we want to find out where the mean of this data is there and how much it is spread. So you just calculate the mean and standard deviation. So for given a data, if you can calculate mean and standard deviation, you basically have learned about the data distribution. So for this data, let's say, assuming if you calculate it, mean and standard deviation, let the value is 5.0 and standard deviation is 1.2. Then once we have learned this, we can generate new data. So how we can generate? So assuming it is follow a normal distribution. So the new data will be nothing but mean plus some random sample you take, assuming follow from normal distribution. So the sample will be in between 0 to 1. You take a sample, you multiply with the standard deviation and add it to the mean, then you will get the new value. Suppose let's say we take 0.5, then if you just calculate it, then the new data is 5.495. So this was the rounded. So if you actually calculate the mean, then the mean of this data will be 4.9 and the standard deviation will be 1.19. So 5.49 means this. So this new data is basically belongs to the same distribution that this data is there. And you can take n number of samples of Z and you can calculate some more data. So this new data points, collection of new data points that we have generated, we can say these two are similar. So this, let's say this is X new and this is your X. So now we can say X is equal to X is similar to X new, because this also follows the same distribution, probability distribution. Okay, so we got the idea. I hope you got the idea of generative AI. So what we want to do? We want to learn the probability distribution of the data. So data distribution. But there is a problem. Can we just, so there are lots of assumptions we have made here. So it follows the normal distribution, and we have just simply calculate mean and standard deviation. The problem is the real world data that we have, like image, text, audio, video, they do not simply small numbers. They are high dimensional data. So in real world, directly calculating mean and standard deviation won't work, because they are high in dimensional. Even one small image that is stored in your mobile is of 1024 into 1024 dimension, which is quite complex. And simply calculating mean and standard deviation is not feasible. Also, it is not like that it only follows the same single distribution. It might be following multiple distributions. For example, if you have let's say structured data, F1, F2, F3, structure means row column data. You have a tabular data and you have number of instances, let's say 1, 2, 3, 4, and so on, and you have n number of features. So each feature's values over the data set, training data, might be following one distribution, and other feature might be following another distribution, and so on. So you might have multi-model distribution, similar to images, where you don't have only one type of image. Let's say in the data you might have image of cat, dog, and horse, and all these images might be following different types of distribution. So the real world data is multi-model distribution. High dimensional data is simply calculating coming up with a probability distribution is not possible. So that's where in the real world we have two types of models of generative AI: implicit versus explicit. I hope you understood. And you can just ping me up. You can just put a message in the chat if you want to move it through. Okay. So now how to? So the core idea is we have to learn the distribution of the data. But how we are going to do it? So in research, researchers in the past they have addressed this learning the distribution problem, also known as density estimation. So that also treated the problem as a density estimation problem. So all the researchers have come up with two types of model. One is the explicit density estimation, and another one is the implicit density estimation. So what they have done in explicit density estimation, you define a distribution function. So you explicitly define a function for data, and then you learn over it. So you come up with a explicit probability distribution function, and then using the training data you learn over this. I'll give you just intuition of it. Whereas an implicit, sometimes it is not possible to come up with a explicit function to learn over it. So why not just come up with some models in some way so that we just provide the data and somehow that model learns to generate the same data, similar type of data. So we're not defining a function. So what is mean by defining a function? Okay, so all the models that comes under the generative models are two types: explicit density estimation, implicit density estimation. Inside this, you have two types of models: traceable density and approximate density. So in traceable density, you explicitly define one function and you learn over it, and you have different models like neural auto density estimation, masked auto density estimation, pixel RNN, pixel CNN, and so on. In approximate density estimation, you have variational autoencoder, which is one of the famous model for generating a new data. And implicit, where you have a GAN, which you have studied on 20th, and Dr. Ashish gave you some insight about the generative adversarial network, how it works. In the implicit density estimation, we are going to see the recent model or diffusion model in today's lecture. So, okay, so we understood, okay, so given some x, we need to find out, we have to come up with the probability distribution of x. And if we can come up with the probability distribution of x, we can sample new data. Right? So we have this point of time, we are clear about. Now, regarding, so even in the toy example, we have seen, we have defined that function as a simple normal distribution, and we just calculate the mean and this standard deviation. In case of image and text, how we are going to define it? So, for example, let's say if I say I want to define probability of an image, probability distribution of an image, how we can define it? Because if we talk about explicit density estimation, where we want to find out, explicitly define a function, in case of image, what can be done? So we can define distribution of an image as an distribution, probability distribution of the probability of the pixels. Right. So one name approach is you just take pixel, multiply with the second pixel, and so on. So for all the pixels, you just calculate the probability distribution and you multiply. But there is a problem. The pixel is not independent to each other. So instead of just simply multiplying the probability of the pixels, we use the conditional probability. So we define the probability of pixel 1, and we define the probability of pixel 2, given some initial pixel, and so on. So basically, and we multiply it. So basically, for each pixel, we define the probability of pixel given all the previous pixels. And for all I, 1 to n, all the pixels, that gives you the probability of an image. And this is the idea that some models have been used, like pixel RNN and pixel CNN. So this is the idea of explicit density estimation. So you use chain rule to decompose likelihood of an image into product of one-dimensional distributions. So pixel of probability of ith pixel given some previous pixels. And once we define this function, we can train over the training data. However, there are two problems. One is the calculation. So how we are going to calculate this conditional probability? So this becomes complex distribution over pixel values. So instead of doing statistically, what we are going to do, where we are calculate the frequency and all, instead of that, what we are going to do, we are going to express it as a neural network. So in initial neural network lecture, you might have studied that using neural network, you can represent any complex function. And the second issue, what we are calling, which of the pixels will be the previous pixels. So for that, we have to define some ordering. Okay, so I'll take this ordering, and then this pixels will be the previous pixels of it. So that is the idea of images. Let's say how we define probability of text. For example, I like this course, and I want to define the distribution of this text. So that usually defined as a distribution of the tokens. And since it is a sequence data, we define probability of I multiplied with the probability of like given I multiplied with the probability of this given I and like, and so on. So we decompose the probability into product of the probabilities of the conditional probabilities of the tokens given the previous tokens. So this type of joint distribution of over text you might have seen in different models like n-gram based models. You can use n-gram based neural network based models like RNN or LSTM. They try to if the language models are built over it, basically they try to learn the distribution of the data. So okay, again, just what we want to do in explicit density distribution, we try to come up with a function, and obviously what could be the function for video? Obviously product of all the frames. How so once you have defined distribution function, you can use it, and that was the idea of pixel RNN and pixel CNN. So they take ordering from top left to bottom right. So for this pixel, there is no previous pixel. However, for this pixel is previous, and similarly for this pixel is previous. So what it does, it treats this problem as a sequential problem, and for each training data, we learn the distribution, and the network is trained either using RNN or LSTM. So once the distribution of the whole image is learned, then a new data can be generated by generating each pixel at a time. So first this pixel is generated, then the second, and so on. The problem was the generation was slow because we are treating sequentially. Similarly, there is a pixel CNN, whereas instead of RNN, you are using the CNN. Now, the idea of previous pixel is basically the size of the window, also known as a kernel. You might have, or the filter. You might have studied in convolutional neural network, where in a particular window, from that window you calculate single value and using element-wise dot product and sum, and then you come up with a feature map. I'm quickly going through this because you might have heard about this in the previous sessions. That also take the previous pixel and using some kernel size, it learns over the image, and again it generates pixel by pixel. So the summary of it, that explicit density estimation models basically come up with a function, and the training is done to maximize the likelihood of the training images. I hope it is clear till this point. One second. Yes, sorry for the interruption. And then one of the implicit density estimation model you have seen, where you have a generator network and discriminator network in GAN model that Dr. Ashish have introduced, where generator takes a noise. It could be a random noise. Basically, it's a vector, random vector, and it generates a sample. And there is another network, and both these networks can be any neural network based models. So, and this discriminator networks takes generated sample known as a fake sample and real samples, and discriminator is try to identify whether it is a fake sample or real sample. So basically, discriminator is just doing the binary classification. And both these networks, depending on the type of problem, they can be any neural network. So the whole idea is once the model is trained, so trained means the generator is able to learn the distribution of the real data, then generator can generate any new data given some random vector. So there is, in this type of model, we have not defined any function. We come up with a setup. Here, this is an adversarial setup. Adversarial setup means you have two players. They are competing with each other, and the setup is something like this. With this competition, generator uh, is become stronger to generate data which is similar to the training data. So I think I don't have to go to this. You might have covered in the Dr. Ashish lecture. The idea of implicit and versus explicit is clear to you? Yes or no? Any question? So we move to this point of time. So generative AI, we want to learn the distribution of the data and how we can learn. So there are two ways: either define a function or do not define a function. Just see the samples and somehow in some way you try to learn the implicitly learn the distribution and generate a new samples. Another way is define a function, given a text, given a image, define a function and then try to learn over. So that was the background of it. Now there is another model and comes under the generative AI models called diffusion model. So all the diffusion models basically they are also comes under the implicit density estimation model. Implicit density estimation means we are not going to define a function. We need some idea, some way that model learns the distribution of the training samples. And you can see here this realistic images. Basically, these are generated by the diffusion models, and all those models, basically, we it has some flavors from different models, like GAN that you have discussed, that you have studied, where you have a generator. What it do? It takes a noise and it gives you image directly. So the idea was that from the noise we can generate image. That was the idea was there from GAN. One more idea that have from variational autoencoder, where you have encoder decoder architecture, where encoder. So okay, so I have an image. You might have seen this. From the encoder, given an image, it learns the latent space, and latent space means uh, for each feature, for example, a encoder architecture, what it does, given an image, gives you a numerical representation known as a latent vector, where you can think of this each value as a numerical representation of some feature of this image. It could be, let's say, color, uh, tone, or size of nose, and so on, color, eye color, everything. So, any properties it can represent, and this compact representation is basically representing that image. Now, this is the idea of autoencoder. In variational autoencoder, instead of learning a discrete latent space, what we are doing, we are trying to learn a latent space. That is, you can think of simply each feature, instead of coming up single value, you are trying to come up a distribution represented by mean and variance. And using this mean and variance, you can sample one latent vector, and then given to decoder, it gives you an image. And there is a problem was with the variational autoencoder called interceptability. So this probabilistic encoder is basically tries to map the distribution of the data into some lower bound distribution called, let's say, normal distribution or Gaussian distribution. So the variational autoencoder basically try to learn a normal distribution from the data, and the mathematics is there, that how it is mapping and why it is feasible compared to interestability of learning the exact distribution. So that comes another approximations, because we are approximating the distribution. If you don't get it, it's fine. It's just an broad idea of uh, types of different models. So from there we got second idea. So first idea was, from noise we can generate an image. From in variational autoencoder, we have an idea that distribution can be mapped into standard distribution or simple distribution, like normal distribution, normal Gaussian distributions. We can map it. So these are the two concepts that have been basically taken up into the diffusion model. So we are going to use normal distribution, that is going to and we are going to map the data distribution as a normal distribution. And the idea of coming from noise to image, that has been used in generative adversarial network. However, you might have studied that with the GAN network, you have different types of problem, like mode collapse and non-convergence. Why this was the problem? Because from directly noise to, we are directly trying to come up with an image. So diffusion models, what they in diffusion model, the idea was that instead of directly generating image from noise, why not we can treat it in a sequential way, or iterative way. Why not just take iteration over it and simply unlike using a direct noise, why not just iteratively remove the noise to generate an image instead of directly generating an image? That was the intuition of diffusion model, and it was seen that this diffusion model can generate high quality of data uh, in comparison with GAN or variational autoencoder. The whole idea of diffusion model was uh, generate high quality data by adding and reversing the noise. So these are the two fundamental aspect of generative AI, diffusion based models, and how they work. They begin by progressively adding the noise to a data set, because we had seen from noise we can create the images. So in diffusion model, what was the intuition? So what we do, we add noise to the data in training data, and we generate the noise, and then in the reverse process, what we do, we from this noise that we have done iteratively in the forward phase, in the first phase, we reverse this noise addition, that is we predict the noise, what was the added, and we try to reconstruct the same data, or we transform the data into new realistic data. So the whole idea was that gradual degradation of the data quality by adding some noise, which and if we reverse that process again, denoising step can reconstruct to original form of original data or the new data. So what we do basically, uh, we do it in two ways. There are two phases basically. So we add the noise into the data, and we come up with a noise, and the same process in the reverse step where we denoise the data and try to come up with the generated data. Though I'll give you an example, then you will understand it. So you can think of this creating a data from noise in a iterative way, something like image sculpting. So you start with a, let's say, a block or simply a stone, and then you are carving it to reveal a beautiful statue. So basically, initially that block of stone is, you can think of it as a noise. And when the carving process, you can think of removing the noise and coming up with a detailed statue. So unlike GAN, you don't have two models. Here we are having only one model that is used to denoising the data and to come up with a high quality image or any text. And because since it does not have two models and it is not a reversal setup, you don't have problems like mode collapse and problem with balancing the two objectives. So now how it is done. So this is a simple example that shows initially a training data that we have. Let's say one of the image from the training data we have. So we have some set of images in the data set. We pick one data, and what we do, we add the noise gradually. So this X0 represents, let's say, original image. Then we add some noise, so that uh, quantity of the noise and how uh, the noise is added, amount of noise is added, is handled by one of the parameter. In notation, you can represent it by alpha, beta, or anything. Here it is represented by beta. So we are saying, okay, so we have added some noise and then you get a noisy data. And in the step 2, you add some more noise into the previous data, and then you get the more noisy data. And that process is repeated for some time step. Let's say for 1,000 time step, we have gradually added the noises, and towards the end you get a fully noisy uh, data, which you can see it is nowhere you can see any images. And you can see here this is beta, basically the noise scheduler, which controls the amount of noise to be added, uh, is changed over time. So here you can see the value of it is 0.02, and starting we have added with a small amount of noise based on that scheduler. The diffusion model basically works in two phases. One is the forward phase, another is in backward, or you can say reverse phase. In forward phase, we add the noise. And in the reverse phase, we predict the noise. So this is like here, this is basically we are talking about the forward phase. So first we corrupt the data by adding the noise gradually, and then later on we try to predict the image from the noisy images. So it's a noise basically. The whole image has been gone and it is replaced by when we saw corrupt image or noise, basically it's a random data which doesn't have any meaning. So yes, initial the image is the actual image, and we add some noise in the data gradually, and that how much noise is going to add is basically controlled by uh, some variable. Here it is called noise scheduler. So that variable controls how much noise is going to add it. And initial phase we add the noise to get a fully a noisy data that the whole pattern from initial data has been gone. So adding the noise is a simple idea. You are just adding the noise in the original data, and the forward process basically add the noise for some t step. Here in this example, it is shown for 1,000 steps, and transform that original image to pure noise. Pure noise, the data with a random data. There is no pattern of the original image. And this process is called the Markov process. Basically, you can treat it, this process as a Markov process. What is the Markov process? So when we call a Markov process, where each step, for example, step times step 2, is basically depends on only the previous one. So basically, x2 is obtained by image x1 and adding some noise. That's alpha amount of noise is added. And similarly, x3 was obtained by adding some noise to x2. I hope forward process is clear. And the whole innovation, basically the idea was there in diffusion model that once we, so basically it's inspired from thermodynamics or diffusion. So for example, you add the in a glass of water, when you drop some drop of colors, then how it spreads and how it creates the noise drop by drop. It makes it uh, into some other form. So unlike GAN, where it is an adversarial setup, or variational autoencoder, where you try to compress the latent space, diffusion model treats the data as a signal which is corrupted by noise. This is your signal data which is corrupted by the noise gradually over the time. And the idea comes that the whole idea of diffusion model is to then this try to learn the learn the noise and try to from noise to go to the original image or a new image. So reverse phase, we take a noise and gradually we predict the noise, how much noise has been added. And instead of, there are two ways you can think of. One, if we know that how much amount is noise is added, so why not just separate that image, separate that noise from the image, and we can get the original image. But this is not the idea of similarity models. The whole idea was not to get the same image. The idea was to get the unique image, and somehow we can make the model to learn to predict the noise. Then it can, from any noise, it can generate a new data, high quality data from that image. Okay, so there are different applications. So it generates high quality data images from random noise. Unlike GAN, where you give the noise and model gives you the image, here it is an iterative process. You remove noise iteratively, so it takes more time. So computationally, these diffusion models require more steps because we are having multiple steps, making them slower than the GAN. Right? Okay. Though the proposed model introduces Gaussian-based noise distribution, so we are using the Gaussian distribution to add the noise. There could be different other ways, maybe possible. That could be a research opportunity for it. So how diffusion model works? Dual phase mechanism. It operates in two phases: forward diffusion and reverse diffusion. So in forward diffusion phase, what we do, we add the noise progressively to the data set in multiple steps. Could be, let's say, an example, it was shown 1000. And what it does, this process gradually degrades the data, turning the image into random noise. And in this phase, the whole goal is to make the data increasingly noisy until it becomes unrecognizable. And then there is a second phase, reverse diffusion phase. We train a neural network. So the whole idea of diffusion model, basically, the model learns during the reverse phase, not in the forward phase. Forward phase is that simply a simple phase. There's no neural network is trained during this phase. In the reverse diffusion phase, okay, so the question is, so in the reverse phase, does the model know how much noise to remove in each step? Is it the same amount is added? Okay. So, okay, so there are two ways to think about it. If the model knows that how much amount is added, how much amount of noise is added, then we can remove it and then we can get the same image. But this is not the idea. We instead of, yes, there's no learning in it. Instead of, what we want to do, we want model to predict the noise, how much amount of the noise is added in the steps to get the previous image. By doing so, network learns the type of noise and amount of noise that has been added. But from your question, there is another point, because we want a prediction, so we want to train a model. So for training a model, we need a ground truth as well. We always define a loss function by some predicted value to actual value, and this loss, based on this loss function, we try to minimize this. This is how we train a model using backpropagation. Here we also need some ground truth. So at each step in the reverse phase, though we are going to see in the upcoming slide, in each step what happens, the model that predict the noise. So let's say at time t, it has predicted noise this, and the actual noise that was added at time t, the difference of this is basically treated as a loss at that step. So that the model is lost. So yes, so we use the noise that was the added as in a ground truth in the forward phase to learn during the backward phase, but it is not directly separated from the images. It is used as a ground truth. I hope you got the intuition. Okay. So in the reverse phase, what we do, we train a neural network by reversing the noisy process. The model learns the denoising data step by step, essentially recovering the original data or transforming into new one. So the network is trained on how to reverse the added noise at each step, and eventually the model generate new high quality data by starting from pure noise and applying the learned reverse process. That's where the model can create high dimensional data during this phase. So this was the intuition. Now we are going to see how it works. So in forward phase, now we are going to see the mathematical detail as well. So in forward phase, the model gradually add noise to given data point, and the idea was to progressively degrade the data. In mathematically, this process represented as a stochastic differential equation, but we can break it down into discrete steps for simplicity. How it is done? Suppose your x0 is your original data, basically the image. The xt represents the data time at data at time step t. For example, x1 at time step 1, x2 at time step 2, and x3 at time step 3, and so on. After adding some certain amount of noise. Then the forward diffusion process basically take x0 to xt, the final noise, where t is the final time step, which corresponding to pure noise. This noise is added progressively in the form of this Gaussian distribution equation that you see. Now, though by looking at the noise, looking at this, so basically this represents the Gaussian distribution, xt, mu, and variance. So basically mean and the variance. So you can see here in the forward process, given xt minus 1, the previous image that represent the distribution of xt given the previous image and represented by in form of Gaussian distribution, where there are two things. This is your mean. One second, please. Hello, Aditi. Okay. So, okay. So this is your mean. If you just map to this equation, this is your variance. Now, what it means basically. So this is basically your probability distribution of data at time step t given data time step t minus 1. Here, if you see here this term, basically what intuition is there. So this basically we are having a Gaussian distribution with mean this and variance this. Here I is the identity matrix. So in other words, each time step t, we are denoising the data x minus 1 with Gaussian noise to get xt. And the level of noise that we are adding is increased over time, and which is controlled by beta of t. This is your control or noise scheduler, basically. So there could be one question whether beta is constant or not. So beta is not constant. We are having a different types of so how we are gradually increasing or decreasing the beta or changing the beta is based on different idea. It could be a linear, it could be exponential or on. So we are going to see about it. So basically, if you do not understood this, should I explain it more? So basically, here the mean. If you see here, what we are doing, we are the expected value of the previous step data. We are multiplying with some factor. So we are multiplying with some factor to change over it, and this variance basically gives you the idea how much noise, the amount of noise is added, and this beta is basically lies in between 0 to 1. And the beta could be any linear or a cosine function. You can take it to change the beta value. So here it just shows an example of different forwarding phase using different types of beta. So linear, you can see here it is degrading some like this into pure noise up till time t10. In cosine, you can see here, so there are different uh, outputs and different variations. And if you're using exponential, this is how it is. It is making it is a noise. So you can use any type of data, any type of way to make the change in the beta value, and you can explore others as well. Depending on the type of data, you can have different type of beta scheduler. So basically, this means if intuition we say, okay, sorry. So this, let me just erase all the ink. If you see this term, basically what it is doing, it is scaling the previous data, and by scaling it, it is shrinking the signal to accommodate the data noise, so that the new data and the previous data is of the same size, but we are shrinking it the previous data and we are adding the data noise. And this basically determines the magnitude, noise magnitude. Larger the beta value will basically add more noise. So the term beta defines how much noise is added at each time step. And typically beta is a small value and it increases gradually over time. And how it is increases basically depends on the value, that type of function you are taking it. It could be linear, it could be sigmoid, how you gradually increase it. For example, let's say if it start from 0.001 at time step 0 to a value to 0.02 at the last time. So equation at step 1, what would be the equation? This will be the equation at original image. Given the original image, the distribution of x1 will be 1 minus beta 1, the square root of this, and multiply with the original image, original data, and the variance, and so on. So here you can see the mean, the value, it is dependent on the previous step. You can see x0 at the time x2, it is dependent on x1. However, variance is not dependent on the previous step. And instead of going detail into the mathematics, this basically the dependency we take do it for the computation purpose. So we do not want to make the computationally infeasible this step. There is another way to see this. If we assume alpha t as a 1 minus beta t, so you can represent distribution of x1 at time step 1 as 1 minus beta t is replaced by alpha 1, multiplied by x0, and so on. If you take it recurrently means if we see the mean at time t, what it will be there? Under root of alpha 1 ki jagah alpha t and x t minus 1. Right? For x t minus 1, again you can write alpha t minus 1 under root of alpha t minus 1 into x t minus 2. If you just take these two together, you can write it alpha t into alpha t minus 1 into x2. And recurrently, you can, if you expand it, you can move to the initial image. So the idea was the image at time t can be represented as a function of at time 0. So that represent, so this alpha t to alpha 1 multiplication, let's say it is represented by alpha bar t. So then the square root of alpha bar t multiplied with x0 basically represent the mean at time t. So basically that's just another way, mathematically we are relating mean of time t to time data to 0, where alpha bar t is basically just the product of all the alpha at all the steps s1 to t. So the idea was, if we know how to calculate the mean from entire thought process, then we can write this equation from xt, instead of given xt minus 1, from the starting image x0 we can represent as the mean and the variance. And using these parameters, mean and variance, you can sample a new data. How we can calculate the new data? For example, let's say xt will be, how we sample it? From Gaussian distribution, mean plus variance into some sample. Let's say epsilon sample is taken. So here what is the mean? Under root of alpha bar t multiplied with x0 plus variance. Variance is nothing but under root of 1 minus alpha bar t. If it is multi-dimensional data, let's say image or video, then you need I. Otherwise, it's a one-dimensional data. You can just directly multiply with the sample. If you want to understand it, so if you just take an example, again a toy example. Let us assume this first image is nothing but a simple 0.5, and we have time step 1000, and let's say we are linearly adding the noise, where beta is increasing from 0.001 to 0.0. So at, let's say, t times step 500, the noisy data, what will be the noisy data? assuming our beta value at 500, which is something in between these two, is 0.01. And alpha bar t, which is nothing but multiplication of all this thing, is, let's say, assuming 0.6. And this is obviously, if you have given the beta, then you can calculate it. The alpha bar t means alpha bar 500. Assuming a sample we have taken at 0.3 from normal distribution, then a noisy data at 500 step will be nothing but alpha bar t square root. That means 0.6 square root of 0.6. Then multiply with the original image, original data. Original data was the try example. We have taken 5 plus under root of 1 minus 0.6, which is this, and here 1 minus this plus into 0.3. So if you just calculate this, it will give something around 4.06, which you can think of the original data was this and the noisy data was this. This is the idea basically. So since we know this formula from 1 to t, we can use it to get the computable equation. So we don't need any neural network for it. So in forward process, there is no neural network. So forward process, we are just gradually introduce the noise to original data, and the level of noise as each time step controlled by the noise scheduler called beta t. At beginning, it is low. Data looks similar to original image, but as the time increases, the data becomes progressively noisier until it becomes the indistinguishable. So the idea is at timestamp t. So let's say you have an image. It generates. So you generate noise for timestamp t. You add the noise, and you can see it becomes noisier. In timestamp 2, this becomes your image, and you add noise, assuming, let's say, you have a linear scheduler, and that gives you another noise image, and so on. T3, and during the iteration, that becomes pure noise. So initially, initial information is completely destroyed at the last time. So in the forward process, initial the image was there at T99, it is totally gone. So I hope at least intuition you had, now you have the intuition of forward process. Yes or no? Okay. So you're saying if the actual noise is the ground truth, then during the backward path, then eventually it will learn the actual noise. No. So if the model is learning the actual noise, then your model is overfitting. It's as similar to a machine learning model. If loss is 0, and then if it is generating the same image or same data, or then basically the model is overfitting. So the idea is we want to minimize the loss so that the new data will be similar to the original data, and not exactly the same data. So we want to minimize it. And that again, mathematically, it has shown that how the formulation of this reverse step is there. We'll come to it. Any other question? So we're taking a 5-minute break, then we'll start again.
Yes, sir.
Meanwhile, if you have any question, you can just write it.
Sir, maybe we can start after 10 minutes. You can take a break of 10 minutes, sir. It's up to you, sir.
Okay. So we can start after 5 minutes. There is no issue.
Okay, sir. Okay, fine.
Yeah.
So participants, please, if you have any doubt,
You can
in the
write it on the chat. I'll respond.
yes, sir. Yes, sir. So in the meantime, please, participants, you write in the chat box so that after 5 minutes, when the session that will start, the sir will answer all the your query.
Okay. Any questions? Okay, तो ये तो हो गया. Okay, so the question is, how is the number of time step decided in the forward? So it's basically an hyperparameter. So it depends. It's an experimental decision. So type of quality of the image that you are getting, and because see, the whole idea of training the model was to make the model stronger to predict the original image. So if you want to make it more stronger, then you can have more number of steps. So then the model will able to generate a high quality of images, more high quality of images if you have more number of steps. But again, that's an experimental based on type of data you have, training data, and based on type of result that you require. So I'm creating bounding boxes for certain classification column. But after bounding boxes, I just extracted the segmented image, then applied diffusion model to enhance. My images did not improve much. Could you tell me the column now the approach to follow? So what you can so am I audible, Pradeep?
Yes, sir, audible, sir.
Okay. So uh, the problem. So why have you
Hello?
tried? Yes. So have Pradeep, have you tried using diffusion model first and then extracting the bounded boxes? Because what it might be there the so not exactly, but might be an issue that once you extract the segmented images, the pattern might be missing, so information loss might be there in the image. So diffusion model might not be able to extract uh, any meaningful conversion from noisy to the basically the images. So though exactly I, I don't know what type of model you're using for diffusion. You can change the model as well. Instead of using a standard model, see the models which can work with low resolution image data set. And other approach, you can you first you produce high small size. Try. Okay, so let's move ahead. So in the reverse process, what we do, we denoising the data, and the goal is to reverse the forward process, diffusion process, the noise was progressively added in order to generate high quality data. So the forward process basically add the noise to the data, and the reverse process learn to reverse this noise step by step. And the idea is by the end of the reverse process, the model is able to generate clean data from noise data. Similar to, but unlike to GAN, similar to, but not exactly to GAN, like GAN, where there is only one step. Given the noise, it generates the image. Here we are iteratively we are trying to generate the realistic output. So basically, if we talk about reverse process, it is just the reverse of the forward process, and it involves learning how to gradually remove the noise at each time step, starting from pure noise to uh, reconstructing the original data. So in forward process, we define distribution of xt given xt minus 1. So basically, your xt is nothing but xt minus 1 plus some amount of noise. Here, we model the reverse process as a parameterized equation where we try to come up with the distribution of xt minus 1 given xt. And by learning the parameter, basically the learning we are trying to predict noise. And the reverse transition is basically model using the any neural network architecture. You can use CNN or some any other depending on the task that you have, which learns to predict the added noise. So basically, it is represented by reverse transition, basically xt minus 1 given xt. Is multiple assumptions. First, we assume that this is in Gaussian, again similar to the forward step, where we have modeled forward step as a Gaussian, and each time step at t, the reverse process is also modeled as a Gaussian, where you have a mean represented by this. So basically, this is the mean of the predicted clean data at timestamp t, and this is your the covariance matrix, again, which represent the noise variance at each time step. How much noise we are adding. This is the prediction that we do, and this is the mean at time step. So in the reverse process, basically the mean is typically modeled by this equation, though again the equation might look complex, but if you just understand it, so if you see here, this xt is your noisy data at timestamp t, right? And this is your noise, the neural network prediction of the noise that is added into the forward pass. This was a predicted noise, and the predicted noise basically is scaled using this term. Sorry, you see here this term, we are scaling this noise. So why we are scaling? So this basically we are scaling to predict the noise to match the noise distribution of the forward process. Once yes. So basically, to match the noise contribution in the forward process, we are scaling this term, and this basically the whole using the scaling, this whole term is nothing but cumulative noise that is added up to timestamp t, and we are subtracting it from xt, right? And again we are scaling it by 1 upon under root of alpha t. So this scale basically denoise the result that we have got after subtracting this to reverse the 1 minus. So this is nothing but to reverse it, which was there, which was we had multiplied 1 minus beta t under root of this into xt minus 1. So to reverse this, we are dividing it. You can think of this can go here, that will become the mean, and so on. So this equation becomes the predicted clean data xt minus 1 based on the noise data xt and the neural network prediction of the noise to this. Basically, covariance is again represented by beta t into identity matrix, so that we use identity matrix so that in each dimension it has the similar scaling. So from x0 to xt in reverse direction, when we start from capital T means the last step, where xt is a random noise, we back propagate to generate the clean data at x0. So each time step, for example, time step t, we have predicted noise is this, actual noise was, let's say something, or alpha was there, difference of this, and summation of this for all the steps is basically gives you the and this loss function can be defined as any other loss, and this becomes your the loss function for this. So final denoising is at towards the end, basically the predicted time. So this is your mean and this is your noise. And this is the loss function, basically predicted noise minus actual noise square of this. So loss function, again, this is one of the way you can define loss function for as per your choice. This is the expected value for over timestamp t, which contributes to your whole loss. And the objective of reverse denoising process to learn the parameter theta that minimize the difference between the predicted clean data and the actual data across all time steps. So basically the reverse process by the learning, basically we are not following the same path the actual forward process have gone. We are following that path, but we are not going that path. So we are minimizing the difference between the predicted clean data and the actual clean data. However, that at the timestamp 0, in the reverse step, the image may be something else. So reverse step start from pure noise and progressively remove the noise as a step. And in each step, model predicts the clean data from noise step xt, essentially the denoising the data. And the predicted noise basically helps to recover the clean data by guiding the denoising process. So this is how so a diffusion model takes an image, it predicts an image, the output of the model is an entire noise. The model predicted to be removed from the input. This noise is later scaled based on the schedule to be subtracted. So you can see here we scale it. So the output value is represented by this, and again it goes again and again, and in the later step, the towards the end you get a high quality image. Now, what could be the model for this? It could be a standard diffusion model that have been proposed in the literature uses U-Net architecture. So U-Net architecture having two-step down sampling and then an up sampling step, because it follows a U shape, so known as an U-Net architecture. We are not going detail of it, but just idea of what different types of model could be. Where this, and it's the convolution neural network based architecture, so you have convolution block as well. Self-attention block is also there. So these are the downsampling blocks, and these are the upsampling blocks, which have upsamples the data. So this is the idea. You might have different types of architecture. So initially, image generation, and after at epoch 0, you have total noise, pure noise. After 50 epochs, you are going to see some amount of information there, and gradually when you increase when you go to the more number of epochs, then you will see the original data, high quality data. So what we had, what you had studied during the GAN, you had a generator and discriminator which competes in a game, and the generator creates the data, and discriminator tries to distribute the reality. Where in diffusion model, a sample is gradually first noised, and then the model learns the reverse process to generate the data. Network architecture, you in GAN you had two networks, generator and discriminator, whereas in diffusion model you have only one architecture that is used for denoising the data. It could be a single network based on U-Net or any other architecture that you, depending on the task again. Here the training objective was the min max game, and here it is basically the score matching. The output style is basically given one noise data and directly it generates an image, which is a single pass, where it is an iterative refinement of the many steps. So this was the intuition of a diffusion model and how it is different from other generative AI models. And there are obviously lots of problems because again there are multiple steps are involved. So inference speed is a issue. Training cost is also there because due to iterations, it requires high training time and GPU uses. Lack of latent space is there, conditional fragility is there. It is not only with the diffusion models, but with any other generative AI models, the evaluation matrices, what could be the best suitable appropriate matrices will be there. It's again an issue because the generated image and the training image, uh, the quantitative way to measure the quality is again challenging, and different researchers have proposed different matrices for it. Model size is basically in diffusion. You have the model size is not appropriate for deployment, but again, if you have a high-end infrastructure, then it is. So these are the some references. So that ends to the diffusion model introduction. And if you have any question, then you can ask. Otherwise, I'll show you a demo of it. So I'll show you two demos. One, how you can use a pre-trained model. So you don't have to do the training, how pre-trained model you can use from Hugging Face, which a library, which a company that provides different libraries of pre-trained models, so that you can use those pre-trained models directly in your application or in your notebook or in your model that you are using. And another which shows the step-by-step how diffusion model is trained. So if you have any question, you can ask in the chat. Meanwhile, I'm stopping the sharing and I'll share my Colab notebook to show the demonstration. So I hope you at least had an intuition of how diffusion model works. Okay, so share this. Okay, I hope it is visible. So this demonstration basically shows use of one of the model based on diffusion called stable diffusion base version 1.0. And in this demonstration, you will see how we can use any model from Hugging Face. So if you go to Hugging Face, this is a company that provides various models that you can use directly, and it has various libraries in it. Some of the important libraries are diffuser. So this diffuser module library consists of various diffusion based models, and it provides some abstraction in terms of pipeline. Using this, you can load any pre-trained model. So using Hugging Face is quite easy. And if you are using LLM based models, generative models like so transformer based generative models like Llama, GPT, or all. So then here you have to change it from diffuser to transformers. So there are 2-3 libraries which are important. So let me write some of the libraries. Like one is the transformer. This is used for all the LLMs, LLM based models, so all the large language models. If you want to use, you have diffuser for diffusion based model. One other library which is provided by Hugging Face, which is most of the time it is used, that datasets that contains various sample datasets to work upon. And there is another library that you normally use, Accelerate, which is to make your program efficient. So basically, if you have GPUs available, so that library gives you a simple way to run your code on GPUs. Here also Google Colab can connect to any GPU. So let's say we are connected to GPU. So till it is connecting, let me show you. So what you can do, you can import any pre-trained model. Here in this case, we have imported Stable Diffusion, and this particular example is for text to image. So the idea is you write a text which is a guiding vector context to generate an image. To generating an image, we are using diffusion based model, and we'll take the text as a prompt. So it is only 3 line of code. So you can see here it is we are importing diffusion using the abstraction called diffusion pipeline. We are from pre-trained models, we are loading Stable Diffusion some base. There's an optional line. If you have a code running on the GPUs, then you can directly map this pipe that you have. Pipe means basically you have the model pipeline that you have loaded. You can pass it to the CUDA, so that goes to the GPU device. Instead of running on CPU, it will run on the GPU. If you run it, so this is basically the architecture of this Stable Diffusion base 1. So how it works? So whatever user prompt you write, it taken by the Fusion Clip text encoder. This is text encoder proposed by the OpenAI. We are using Fusion means we are not changing the weights, so it will just take the prompt and it will generate an embedding. That embedding is given to the text condition latent unit. So basically, this is your denoising model is there. So this denoising model takes the noise, Gaussian noise. Together we add the text embedding as well for the guiding, and that generate the condition latent, and we use variational autoencoder to generate an image that gives you 512 to 512. So, and it is repeated for n number of steps to generate a high quality image. However, this was the theory. For using it, you don't have to do anything. Once you loaded the model, let's say in the variable pipe, what you can do using this, you can just pass the prompt. Let's say we have written prompt like a flying horse. So that will give you number of images. And out of those images, you will see higher images. 3 lines of code. What we have done? We have used the appropriate library from the Hugging Face. In case of diffusion-based model, we have used the diffusion. I hope it is clear. While my voice is clear. Am I audible? Yes or no? Am I audible? Okay. So we are using only 3 steps here. In this case, you import the appropriate pipeline. In case of transformer, you have a pipeline. In case of diffuser, you have diffuser pipeline and so on. Using that abstraction, you can load any model, and then you can just pass the prompt and you can use that model. As simple as that. And that will generate an image. So if you say if we can run it, so let's run it. So that will, and you can play with it with different types of that will load this stable diffusion model from Hugging Face, and after one you will see the configuration for this this text encoder and text unit. You will see here the pipeline is shown here, how the models combined together. Still running, takes time. Okay, so it's still running. How much time it will take? So let me show you another example where we are not using any pre-trained model. We are going to use anime dataset. So anime is the cartoon characters we have, and we'll train a diffusion-based model to learn the distribution of that and generate similar data. So if you see here, this particular cell, basically we are downloading that data anime dataset So if you see, if you go to this link, you will find out some anime characters are there. You can see here. So we are going to learn a diffusion model that going to generate the same data. So this particular cell is nothing but using the Kaggle. We are downloading the data. If you're not using this module, Kaggle Hub, you can just directly first manually download it and then you can upload it. This particular cell, basically, we are using, so there are two ways to write the code. Either you can use the PyTorch library or you can use the Keras. Both have their pros and cons. Here in this version, we are using the PyTorch library. So under the PyTorch, you have Torch Vision. Inside the Torch Vision, you have transform module, which is basically for pre-processing the data. And this particular is for the loading the data from the folder. And this is basically data loader is used to create the data into batches. And so we have used the batch size of 100. Once we have loaded and downloaded the data, what we are doing, so we are defining how to transform this data. So normal pre-processing. And first, what we are doing, we are gathering the data and using the dataset loader, we are creating the batch size of 100. So at each iteration, we are going 100 batch at once. So this is for loading and transforming the data. This is basically we are viewing the data. So first 60 images we have seen, and each of with size of 32 cross 32. Only 16 images we have shown. What are the data is there? We have shown here, and here, okay. So here it is. It is the code is shown here for the steps. So you can see here from the theory we have seen. So okay, so this line of code, if you are having GPU, then this line of code, what it does, it automatically transfers the code to GPU and then it runs there for the faster execution. If you see here, we are having parameters. As we had discussed, number of steps we have defined 1000, beta start and beta end we have defined, and we are having a linear schedule, how it is going to change it. And we had defined an alpha parameter as well. And then the square of it, square minus alpha of this. Directly we have got into the variable, so we don't have to write the whole equation somewhere. So we have to write the whole. And for each time step, given x0 and t, we had seen in the theory as well, given the initial image, and if you know the time step and you know the alpha and beta, then you can calculate the time image at time t. So this is this function we have defined to get noisy images. And here we have defined our simple unit architecture. So this is for, you can see here some down samples, then some convolution operations are there, then up samples and so on. So that is there here. And the forward phase, when we pass an image at timestamp t, basically is give you the image. So that gives you the model that you get it. You are referring it to TD using the model And once you define the model, then you define the parameters like optimizer, learning rate, number of epoch, and this is your main training loop that is there. So for timestamp T, you take some sample noise, and you get the noisy images by passing that image and the noise. Then you get the noisy image, and that noisy image, when you pass to the model, you get the predicted noise, and loss is defined by the predicted noise and the noise, the loss function that you define. And then you backpropagate, and PyTorch provides you those functionality and backward and the step to perform the backpropagation. And this line of code is basically for each 10 batches we are printing the loss. So this is for 5 epoch, it is training. I'll not run it because it will take time. And once it is trained, here we have defined a function to sample it. So we are providing default value of 16. So when we call samples, it will create a 16 samples. So from the model learn, we are predicting the noise, and we are updating. So we're getting the X, the first value, and this shows some of the images. Now you can see this is nowhere near to the anime images that we have seen, but so why we have not seen the same images? Because we have run it for only 5 epochs. If you run for, let's say, 1000 epochs, then you will see the images similar to the images that are there. So I just provided you overview of it. You can play with it. I will share the link in the chat. So you can change the parameter, map it with the theory to so this is the let me share this book as well. Let me share this book. So you can see this and make a copy and explore it, understand what each function and each line is doing. So that is the end of the lecture from my side. If you have any question, you can ask. So I've shared the link of both the notebooks in the chat.
Yes, sir. Thank you, sir. Thank you. So yes, participants, if you have any doubt, then please write in the chat box.
So yes, I have given you the answer. So for the same question that you have asked earlier, Pradeep. So actually the problem might be because you are extracting the segmented image from the original images. So the problem is once you extract the small images, the diffusion model might not work because somehow the diffusion model works based on the concept of reproducibility. So you are adding the noise and then denoising the noise. So denoising the noise to get the images. Somehow it is missing the pattern. So the number of ways. So either what you do, you first apply the diffusion model to first convert it to high quality images and then segment it, or maybe you see explore the diffusion models that works on low resolution data set. Low resolution data, then you might get this. Okay, I think we can end it here.
So, yeah, so you don't have that wind up the session here. So, thank you. So we truly so we and you. So thanks, sir, which you attend this session nicely. Thank you, sir. Thank you very much.
Thank you.
Thank you. So yes, participants. So the next session that we will start at 12:30. Okay. So now you have 25 minutes break.